What do aldehydes and ketones have in common, and what makes them so reactive? It's the carbonyl. The carbonyl looks neutral and happy, but that pi bond is capable of resonance, where the pi bond electrons will collapse up onto the oxygen atom, giving me a less stable resonance structure. Oxygen had 2 electron pairs and now gets a 3rd pair from that broken pi bond for a total of 3 lone pairs and a formal charge of -1. Carbon used to have 4 bonds, now has an incomplete octet with a charge of +1. This resonance form has separation of charge and an incomplete octet on carbon, making it unstable, but the resonance hybrid is an in-between of the two, where that pi bond is resonating up and down, giving oxygen a partial negative and carbon a partial positive. This partial positive makes the carbonyl carbon a reactive electrophile susceptible to nucleophilic attack, which is what you're going to see with many of your aldehyde and ketone reactions. So what's the difference between an aldehyde and a ketone? Yes, they both have a carbonyl carbon, but the ketone has 2 R groups, one on either side of the carbonyl, while the aldehyde has just 1 R group and then a terminal hydrogen. The aldehyde is sometimes written as RCHO. R tells me the R group that is attached to carbonyl. CHO is in order carbon bound to a hydrogen, double bound to the oxygen, not to be confused with COH, which tells me that I have an alcohol. The ketone can be written as RCOR, telling me I have an R group bound to a carbon, double bound to oxygen, and another R group. To identify the aldehyde or ketone, look at your molecule, find the carbonyl, and then see what you have attached. If it's an R group on both sides, you know that you have a ketone. If you have just 1 R group and a hydrogen, that's an aldehyde. Sometimes you'll see the aldehyde with an invisible hydrogen, but if the carbonyl is terminal, meaning there's no R group on the side, that's still an aldehyde. For naming aldehydes and ketones, we'll use the method that I teach in the nomenclature series linked below, starting by identifying your parent chain and numbering to give you the total lowest set of substituents. If your carbonyl is terminal and the highest priority functional group, that is automatically number 1. I have a total of 4 carbons giving me a first name of bute, only single bonds in the parent chain giving me a last name of ane. My functional group is terminal with a hydrogen at the end, making this an aldehyde, giving me the ending on carbon 1, al for aldehyde, but the aldehyde is a terminal functional group, understood to be at carbon 1, and so we don't use the number, just the suffix al. Then you want to account for any substituents, in this case a methyl on 3, giving me 3-methyl. We put the name together, substituent, first name, last name, functional group. But when your functional group starts with a vowel, you drop the E in the last name for a final name of 3-methyl butanal. This next molecule has a carbonyl with R groups on either side, making it a ketone. We name it the same way, starting by identifying the longest carbon chain and numbering it on the side that'll give me the total lowest set of substituents. This molecule has 6 carbons in the parent chain, giving me a first name of hex, only single bonds giving me a last name of ane. My functional group is a ketone, giving me the suffix, the last name of ONE. And because it's not terminal, I have to include the number for 2-one. And finally, I have an ethyl substituent on carbon 4. Since my functional group starts with a vowel, I drop the E in ane, putting the name together as substituent, first name, last name, functional group suffix, giving me 4-ethyl, drag the 2 in front of the name for 2-hexanone. Or some professors will also keep the 2 where it is, and in that case you don't drop the E because you no longer have one vowel following the next, for a name of 4-ethyl hexane 2-one. If the carbonyl is reactive at the partially positive carbon, which is more reactive, the aldehyde or the ketone? Reactivity at the carbonyl carbon depends on the nucleophile being able to attack that carbon. Since the ketone has 2 R groups, the carbonyl carbon is blocked. It's more sterically hindered, making it less reactive, but the aldehyde, having only 1 R group and a small hydrogen, is less sterically hindered. The carbonyl is more accessible, making it more reactive. Don't just watch this and think you get it. Use my Aldehyde and Ketone Worksheet to practice identifying structures and their reactions. Comment worksheet below and I'll send you the link. Another thing to consider is that carbon is an electron donating group. That means the R group on the carbonyl is donating negativity towards that partially positive carbon. If a ketone has two R groups, both donating negativity, that carbonyl carbon is a lot more balanced, a lot less reactive. But the aldehyde having just one carbon, just one electron donating group, the partial positive is not canceled out as much, making it a lot more partially positive and a lot more reactive. For example, in this reaction, I have a methyl grignard that attacks the aldehyde carbonyl carbon. Yes, there's steric hindrance on the left side, but there's nothing here blocking the grignard, and so it easily attacks and kicks up that pi bond. How do aldehydes and ketones react? That's what we'll cover in the next video, linked below, or on my website, leahversailles.com/aldehyde ketone.